Okay, this is the fourth lesson in the motion topic, and I'd like you to begin by pausing the video and having a go at the quiz. Okay, check and correct your answers, so pause this and check and correct, and the next slide has got the last few answers on. So yeah, pause this and check and correct these. Okay, so far we have looked at speed. We've looked at calculating speed given a certain distance and a certain time. We've looked at representing different speeds with a distance time graph. We've looked at what a flat line means on a distance time graph, and we looked at some journeys. And we looked at the speed of particles and the speeds of waves, which was really interesting. And that's kind of one application. That's one reason that we're learning about motion, is so we can apply it to different things that we know about. So today's lesson is moving on from speed. We're going to be talking about acceleration. Okay, let's start by having a look at a distance time graph. So we've got distance on the y-axis measured in meters and time on the x-axis measured in seconds. So let's have a look at two graphs, two lines. There they are. And there's quite a lot that we could talk about now that we've got these two lines on here. I want you to just pause the video and see if you can think of anything you could say about those two lines. Could you compare the speed of them, even without doing any calculation? Could you do a calculation? Could you find the speed of both of them? Let's have a look then. So let's start with the red line. I'll use a red pen. Now let's remind ourselves that speed is equal to the distance covered divided by the time taken. Speed equals distance divided by time. So let's have a look at the red line. Speed is measured in meters per second, and that means how many meters does that object go every second. So if we look at just 1 second, from 0 to 1 second, and then if we look at the line up here, we can see that in 1 second this object has moved 2 meters. This means that the speed is 2 meters per second. It moves 2 meters every second. Let's have a look at the green one. So let's go across to 1 second again. We want to find out how many meters it's gone in 1 second. We can go up, and it's about 4.5. It's about 4.5 in the middle there, between 4 and 5. So the speed of the green one is 4.5 meters every second. That means that it travels 4.5 meters every second. Now, we can do that calculation. I've just done it, and we can see that the red one is going slower than the green one. Now, if I didn't have numbers along the bottom, I would still know that. I would still know that the green one was going faster. And that's because the green line is steeper. It has a larger gradient. It covers more meters every second than the red one does. That's an interesting thing and something very, very useful for today's lesson. Okay, we're going to have a look at a journey now, and we're not going to have any numbers. We're just going to do this describing the speeds relative to each other. So here's the first one, here's the first section of the journey, and whenever I talk about a journey, whether in more than one stage, I like to put a little number above it just so that I know what I'm talking about. So we can see in section 1 here that the object is moving. It's not moving very fast, but it is moving. I know that because it's covering a certain distance in a certain time. The line is not flat and therefore it must be moving. Section 2 here. Let's find a blue. Section 2. Now, if I compare section 1 and section 2, I would say that section 2 is moving faster than section 1. So it's the same object, but in section 2 it's moving faster. And I know that because the gradient is steeper, the line is steeper. There are more meters being covered per second than there were before. And finally, section 3. So section 3, I can say, is going faster again. So section 1 was going quite slowly, section 2 is going faster, and section 3 is going even faster. Now I knew that without even calculating anything, because the gradient is getting steeper every time. The line is getting steeper every time. So this shows an object getting faster and faster over time. Let's have a look at this one then. So we've got another slow speed to start with. Next section gets a little bit faster. Next section gets a little bit faster again, and faster again, and faster again. Now, and faster again. Now what this shows is that the speed is changing over this whole period of time from here, from 0 to about here. The speed is increasing. It's increasing and increasing and increasing. And it takes about this much time for the speed to increase. So here it might be going at 5 meters per second, then it might go at 8 meters per second, then 10 meters per second, then maybe 15 meters per second, then 20 meters per second, and here maybe 25 or 35 meters per second. So this shows that the speed is increasing, increasing, increasing. It's getting faster and faster and faster. Now, if this were to happen over a very short amount of time, if a car was or an object was going to get quicker over a very short amount of time, it might look like a curve. A curve on a graph is just made up of lots of short, straight lines that gradually get faster and faster and faster. We have a word in physics for something that gets faster and faster and faster. We say it is accelerating. We say there has been acceleration. So a curve like this on a graph, on a distance time graph, shows acceleration. Acceleration is something that's getting quicker and quicker and quicker. The speed is increasing over time. Let's have a look at a different journey. This is section 1, and I would say that this is going quite fast here. In section 1, this object is moving quite fast, and I know that because the gradient is quite steep. In section 2, I can see that the object has slowed down a little bit. It's still moving, but it's going at a slower speed. And I know that because the gradient is less steep. In section 3, I can see that it's going even slower. So this object is going fast, then slow, then even slower. Here, it's actually stood still. Time is still happening, but distance isn't changing. Therefore, the object must be stood still. So this shows an object slowing down. It was going fast, then it goes slower, even slower, and then stood still. If that happened quicker, if it happened over a shorter period of time, it might look something like this. And hopefully you can see that if this change in speed happens over a short enough time, the line will end up looking like this. It will look like a curve. And a curve is just a series of straight lines, but they're very, very short and they're all joined together. So you can see that as we go up, the gradient of the red line that I'm drawing on top is getting less and less and less. And eventually up here, the gradient is 0, and that shows that the car or object is stood still. This shows an object slowing down. It's getting slower and slower and slower. And in physics, we call this deceleration. I'd like you to pause the video and have a go at these questions. Question 1 asks you to say what does this line show on a distance time graph? And then the extension, could you give a real life example of what the line might be showing? Okay, so a straight line like that shows that an object is moving at a constant speed. That means the same speed all the time. A curve like this for B means something is accelerating, which means it's getting faster and faster and faster. C, a straight line like that, means it's still or stationary, not moving. And D shows an object decelerating or getting slower and slower and slower. Okay, we can use our knowledge now to describe the journey of an object using a graph. So let's break these into sections. Let's have the red section is section 1, the green section is section 2, and the blue section is section 3. In section 1, the line is straight for the entire section. It's also quite steep. This tells me that the object is moving at a constant speed, the same speed that's quite fast. So constant, fast speed. In section 2, I can see that at the start of section 2, the gradient's quite steep, but by the end of section 2, the gradient is quite shallow. This tells me that the object is slowing down, and the word we use for that in physics is decelerating. Decelerating, getting slower and slower and slower. And in section 3, this is a flat line, and so this tells me that the object is standing still, not moving. And so that's how you describe a graph. That's how you describe a journey using a graph. I'd like you to pause the video now and have a go at describing these journeys. Okay, check and correct that you got the right answer. If you want to, you could make up a little story, a real life story that goes along with each of them. Okay, let's have a look at this car. If you imagine driving this car, you might say that it can go from a low speed to a really fast speed really quickly. Often when people discuss Formula 1 cars or sports cars, they discuss how quickly a car can go from 0 to 60, and that means from 0 miles per hour to 60 miles per hour. When they compare that, they're talking about how good it is at accelerating. So a sports car like this will have a really high acceleration. If we look at the blue car, I can see immediately that it's going to be less good at accelerating. It's going to take a longer time to reach a higher speed, so it's going to have a lower acceleration. Let's have a look at the graphs for these. So for the sports car, the graph might look like this. So we can see the first red section down here, it's going quite slowly. That's quite a shallow gradient. And at the end, it's going really fast. Now, this is the change in velocity, the change in speed. So down here we're going at a slow speed, and up here we're going quite a fast speed. And down here on the time axis, this would tell me how long it takes for the car to go from the low speed to the high speed. If we compare it with the graph for the blue car, it might look like that. So here we have a low speed and a fast speed. And instantly I can see that it takes a longer time for the blue car to reach this fast speed. If I look down here on the x-axis at time, it takes all of this time for that blue car to accelerate to this speed. It also covers a larger distance. Let's compare the distances. So the red car, the sports car, covers this much distance, and the blue car covers this much distance. So I can see that the red car can change its speed more quickly, and therefore we say it's got a higher acceleration. So we can calculate the acceleration of an object, and the way we do that is we say that acceleration is equal to the change in speed divided by the change in time. So we compare the original speed and the final speed, and we look at how long that has taken. If I wanted to use symbols instead of words, I would use a, lowercase a, for acceleration. I would use this triangle here is a delta, and it stands for change in. And then S for speed, and delta or change in, T for time. Now let's have a look at the units for acceleration. So the unit for speed is meters per second. Meters per second. That means meters every second. And the unit for time is seconds. So acceleration is equal to meters per second per second. So I can write that in a number of ways. Meters per second per second. I can also write that as meters per second squared. And I can also write that as meters per second squared. All of those three ways of writing the units mean the exact same thing, and you can use any of them. So a bus accelerates from 5 meters per second to 25 meters per second in 10 seconds. What was the acceleration? So the change in speed from 5 to 25, the way we work out the change is we do the higher number take away the lower number. So 25 take away 5. So the change in speed is 20 meters per second. The time, the change in time, is 10 seconds, and we want to find the acceleration. So acceleration is equal to the change in speed divided by the change in time. In this case, the change in speed is 20 and the change in time is 10. And so my acceleration, 20 divided by 10, is 2 meters per second per second. I could also write that as 2 meters per second squared, or I could write it like this. Any of those is correct. So this time I've been given the acceleration of a car, 10 meters per second squared, in 20 seconds. I've been given a time. So acceleration is 10 meters per second squared, and the change in time is 20 seconds, and we want to find the change in speed. So acceleration is equal to the change in speed divided by the change in time. So I can write down 10 for acceleration is equal to the change in speed divided by 20. Now the way we solve this is we times both sides by 20. So I'll do 10 times 20, and that's going to give me the change in speed. So the change in speed is going to be 200 meters per second. So this question says, how long does it take my car to go from 4 meters per second to 10 meters per second if it has an acceleration of 2 meters per second squared? So let's write down what we've been told. We can do the change in speed, and that's the larger number take away the smaller number. So that's 10 take away 4. So the change in speed is 6 meters per second. We've been given the acceleration of 2 meters per second squared, and we want to find the change in time. So my equation is that acceleration is equal to the change in speed divided by the change in time. And acceleration in this case is 2 meters per second squared. The change in speed is 6 meters per second, and we want to find the change in time. Now in this case, to find the change in time, I'm going to do 6 divided by 2, and that's going to give me the change in time. And so the change in time is going to be 3 seconds. Okay, have a go at the worksheet. Make sure you show your workings out for each question.